Hello. Now let us discuss Charpet's method for solving partial differential equation. We solve a nonlinear partial differential equation of first order. Nonlinear means we have small p and small q that are dou z by dou x and dou z by dou y that occurs other than first degree. That means their multiple and their powers will occur in the equation. Such equations are called non-linear partial differential equation. Okay, so first order. So we are discussing of first order. So it is of the form f of pq equal to 0, where p and q are equations containing p and q are some partial derivative dou z by dou x and dou z by dou y. Then the complete solution is given by z is equal to ax plus by plus c. So it is in different form also. We will discuss that in coming slides. Using Charpet method, we solve the partial differential equation which are non-linear, and we'll solve the equation of the form f of x, y, z, pq equal to 0, and we know that dz is equal to dou z by dou x dx plus dou z by dou y dy, which is equal to p dx plus q dy, which is the chain rule. Okay, as we did in the previous case, we can form Charpet's auxiliary equation or Charpet's equations by creating subsidiary equations like dx by minus dou f by dou p equal to dy by minus dou f by dou q equal to dz by minus p dou f by dou p minus q dou f by dou q equal to dp by dou f by dou x plus p dou f by dou z equal to dq by dou f by dou y plus q dou f by dou z equal to dou phi by 0. Okay, so in simple form we can write dx by fp. Fp means dou f by dou p equal to dy by minus fq equal to dou dz by minus pfp minus qfq equal to dp by fx plus p fz equal to dq by fi plus q fz. The last term we generally not consider for solving, but you remember that also. We will make use in some case. Okay, so by the previous case we will group and try to separate variables and then integrate to find the solutions. Okay. Okay, now the working rule for Charpet's method is, first of all we convert the given equation as some different form, which is f of x, y, z, p, q equal to 0. F of x, y, z, p, q equal to 0. Make an equation like this, and then we differentiate each part. So as we have to find terms in the subsidiary or auxiliary equation, which are auxiliary equation for this Charpet's method is dx by minus fp equal to dy by minus fq equal to dz by minus pfp minus qfq equal to dp by fx plus pfz equal to dq by fy plus qfz. So we need to find each and every portion of this equation, subsidiary equation, each and every portion of the subsidiary. That means we need to find fp from this given equation. We need to find fp, fq, then fx, fy, fz. That means we need to differentiate given equation partially with respect to x, given equation partially with respect to x, and given equation partially with respect to y, with respect to p, with respect to q, with respect to z. Then you choose two proper fractions to find integral, so that it simply separates variables. And then what you need to do is you need to write at least simple relation with p and q. Okay, simple relation for at least one of p and q. Then you need to write the given a particular form. dz is equal to p dx plus q dy. Then you integrate and find the solution. So we'll examine in detail in some given example. Okay, now let us solve one question. In this, we are asked to find solution of partial differential equation by using Charpet's method. The question given was z is equal to px plus qy plus p square plus q square. Okay, so first of all we need to see this particular question, and we can say that this is a non-linear partial differential equation by seeing this p and q. It is having higher powers. Okay, so now we can rewrite this particular equation as z minus px minus qy minus p square minus q square equal to 0. So this is of the form f of x, y, z, p, q equal to 0. Now we can think about auxiliary equations, Charpet's auxiliary equations, which are dx by fp minus fp or dou f by dou p equal to dy by minus fq or minus dou f by dou q equal to dz by minus p fp minus q fq equal to dp by fx plus p fz equal to dq by fy plus q fz. Okay, we have the given equation z minus px minus qy minus p square minus q square equal to 0. So next what we need to do is we need to find all these partial derivatives. That means we need to find dou f by dou p, dou f by dou q, and then dou f by dou x, dou f by dou y, and dou f by dou z. Okay, so we need to find all these separately. So let us find dou f by dou p first. Since this is the equation, so we can clearly say that dou f by dou p is equal to minus x minus 2p, and dou f by dou q is equal to minus y minus 2q, and dou f by dou x is equal to p, dou f by dou y is equal to minus q, minus q. Then dou f by dou z is equal to 1. So then what we need to do is we need to substitute all these partial derivative that we have found into the equation, the auxiliary equation. Okay, so what we get is dx by minus of minus x minus 2p equal to dy by minus of minus y minus 2q equal to etc. Okay, so in this, first of all we need to see here that check the last term. Okay, check the last two terms, that is dx by dp by 0 and dq by 0. So since these all fractions are equal, let us equal to this equal to lambda. That means df by and dp by 0 equal to lambda and dq by 0 equal to lambda. That means dp equal to 0 and dq equal to 0, which implies integrating this gives p is equal to some constant, arbitrary constant a, and q is equal to some arbitrary constant b. Okay, now what we need to do is we have combined this into the equation dz is equal to p dx plus q dy. Here p was given as a dx plus b dy. Now integrating, what we get is z equal to ax plus by plus some constant, okay, some constancy, fine, where a and b are arbitrary constant. Also, in this particular case, you can also substitute these values back to the original equation that is given in the question. Z is equal to px plus qy plus p square plus q square. So you can substitute p equal to a and q equal to b in this equation. Then also you get px plus qy plus a square plus b square, where a, b are arbitrary constant. Even you can write a square plus b square equal to c. So we get the same equation. Now let us solve another partial differential equation, which is a nonlinear partial differential equation, by using the same method. Okay, so the question was given as q equal to 3p square. So this is clearly a nonlinear partial differential equation. So first of all, what we need to do is we have to convert this equation in this form: f of x, y, z, p, q equal to 0. So we can convert this as 3p square minus q equal to 0. Okay, so this is our f function. So now we have to write all this Charpet's auxiliary equation. So this is the standard equation. You have to make sure that you remember this equation. So in this we have to find fp, fq, fx, fy, fz. Okay, so these all terms we have to find. So first of all, let us find fp. Fp is nothing but dou f by dou p is equal to, from this equation it is equal to 3 into 2p, that means 6p. Now we can find fq is equal to dou f by dou q equal to, since it is given as function is 3p square minus q, so it is equal to minus 1. Okay, similarly we can write fx is equal to, here no x terms, so equal to 0, fy equal to 0, and fz equal to 0. Okay, now take the last two fractions, that means these two, dp by 0 equal to dq by 0. So this is of course equal to lambda, therefore dp equal to 0 and dq equal to 0. We can write p is equal to some arbitrary constant a, q is equal to some arbitrary constant b. Okay, now our function was f is equal to 3p square minus q equal to 0. Okay, so that means we can write q equal to 3p square, or we can write q equal to, since p is equal to a, q equal to 3a square. Okay, now we write dz is equal to p dx plus q dy. Here p is a, that is equal to a dx plus 3a square dy. So now we can integrate to get z is equal to ax plus 3a square y plus b, where b is some constant. So this is our solution, where a and b are some arbitrary functions. Okay, now let us see another problem. Solve a partial differential equation p square plus q square into y equal to qz. So again we convert this equation into some form of f of x y p z p q equal to 0. So ultimately what we get, this is the our function. Okay, now uh, we can consider the subsidiary equation or Charpet's auxiliary equation. So we can write this subsidiary equation. Then you can find each and every term, fp, fq, fx, fy, fz. Okay, we have to find each and every term. So first of all, let us find fp. Since the given equation is of the form this, so fp is equal to 2py. Okay, and fq is equal to 2qy minus z. Okay, then fx is equal to 0, fx is equal to 0, fy is equal to p square plus q square, and fz is equal to q. So we can substitute all these terms into the subsidiary equation. Okay, then what we get is, we consider these last two terms, okay, which are dp by minus pq equal to dq by p square, where you can cancel one p from both sides. So then you cross multiply, what you get is p dp equal to minus q dq. So otherwise you can integrate this directly to form p square equal to minus q square plus some constant, or you can say p square plus q square equal to some constant, say c square. Okay, now we can substitute instead of p square plus q square, we can substitute c square. Okay, so what we get is c square y is equal to q z. That implies q equal to c square y divided by z. Okay, now we can substitute this into again the equation p square plus q square equal to c square. Okay, so that we get p square plus, instead of q square, c square y by z square equal to c square, or p square is equal to c square minus c square y by z whole square. Okay, that is c square minus c raised to 4 y square divided by z square. So now you can take as common factor z square c square minus c raised to 4 y square divided by z square. Okay, so you can take c square also outside, c square into z square minus c square y square divided by z square, which is equal to p square, right? Now p becomes, p is equal to c by z into square root of z square minus c square y square. Okay, c by z into square root of this thing. So now we get p and we also get q. Okay, we get p and q. So we can form the equation dz is equal to p dx plus q dy. So we can substitute p here, c square y by z dx plus c by z into square root of z square minus c square y square dy. Okay. Since now we got p and q, you can form the equation dz is equal to p dx plus q dy, where p is equal to c by z into square root of z square minus c square y square plus q is equal to actually c square y by z dy. Okay, now we can take this as z dz is equal to c into square root of z square minus c square y square plus c square y dy. So here we can see these variables almost separated. So also we can maybe take this as z dz minus c square y dy equal to c into square root of z square minus c square y square, okay, into dx. So now you can take this as one side, so equal to c dx. You can keep this side, and other side z dz minus c square y dy divided by the square root term, square root of z square minus c square y square. So this becomes a formula where you can directly try to find the value, where this can be integral of some value. Okay, this is what you get finally. So we have to integrate now. Okay, before integrating, so we use a technique whether we can write this in form of a derivative, so that derivative of integral becomes a function itself. So we'll start with the denominator. So we'll try to find a derivative of square root of z square minus c square y square. Okay, so this is nothing but derivative of z square minus c square y square power 1 by 2. Okay, this is equal to 1 by 2 into z square minus c square y square power minus 1 by 2 into derivative of the function inside, that is 2 z dz minus c square into 2y dy. Okay, so we can rewrite this as 1 by 2 into z square minus c square y square power minus 1 by 2 into 2 into z dz minus c square y dy. Okay, cancel these two, so what remains is z dz minus c square y dy divided by square root of z square minus c square y square. See this, actually this is derivative of the function set is square root. So derivative of integral becomes that function itself is, so that this is derivative of integral of this thing becomes, this is actually what we need. So that when you integrate, this is nothing but this implies equal to integral derivative of square root of z square minus c square y square equal to integral c dx. So this becomes square root of z square minus c square y square equal to cx plus some constant. When you can square and get the answer some more good manner, which implies z square minus c square y square is equal to cx plus a the whole square. Or you can take this thing outside and write the function as z square equal to cx plus a the whole square plus c square y square, which is the required answer. Here I mistakenly put 1 by 2, so you just overlook that.